Good evening, Carmarthenshire. This is Astrophotography, and as you can see from the subtitle, what I'm talking about is photographing interesting objects in the night sky, but preferably without using ridiculously expensive equipment. So I'm going to say a little bit about how you can start simple if you fancy getting into the idea of photographing objects that are up there, what you can do with simply a camera and a tripod. And then, despite the title of the talk, I will talk about some ridiculously expensive equipment. If you do want to buy yourself a telescope, small telescopes might cost hundreds of pounds, but large telescopes can cost many, many thousands of pounds. And I'll have a little look at telescopes and mounts. But then I'll be looking at the sort of equipment that I really want to talk about this evening, which is the cheaper end of the market, what you can do with a camera and what I call a star tracker, which I'll explain in just a little while. And then I'll show some of the images I've taken so you can get an idea of what you can do with a relatively small amount of equipment. And I'll finish with what you can do if you want to get away from the street lights or other areas. Perhaps in Wales it's not so bad, but here in close to Liverpool we have quite a lot of light pollution. So I'll say a little bit about what you can do if you take a holiday under very dark skies. So firstly, let's start with just a camera and a tripod. What sort of images might you be able to get? Well, this was taken quite a few years ago. This was taken before I had a digital camera. So this is taken with a good old-fashioned 35mm camera and slide film. And it's a picture simply putting a camera with a wide-angle lens on a tripod, pointing it north and taking a 5-minute exposure. This was taken not from the UK, but was taken whilst I was on holiday, having a look at the pyramids and other areas around Egypt, and in this particular case moving over the border into Jordan. So Polaris is relatively low in the sky. There's Polaris in the centre of the image. In 5 minutes it's not moved at all, well basically not at all, because Polaris is the star very close to the North Pole. So as the Earth turns, the stars appear to rotate around Polaris, and Polaris seems to stay essentially fixed in the sky. But you notice that all the other stars have formed little trails, and the further we go away from Polaris, the longer these trails become, because the Earth has turned a certain amount in 5 minutes, and so the more distant stars from Polaris appear to be little star trails. And the star trails are quite short for those stars close to Polaris. And of course there's no reason why we should limit ourselves to 5 minutes. But the beauty of digital photography, which we can now do with our digital cameras, is we don't have to leave the shutter open for a long time to see the star trails. We can, if we wish, take a series of short exposures and then add them all together using pieces of software. Shall I just admit this person, or? Okay.
Did I get a bing bong? You just carry on, I'll just look.
Okay, I still get windows coming up on my screen.
All right. I don't think we can do anything about that.
Yeah, okay, let me just get rid of that. Okay. So with digital photography, we are not limited to taking one long exposure. We can take a series of short exposures and add them together in software. And I've done that for a much longer equivalent exposure of 6 hours. And now we have somebody else wanting admission. Okay.
No, I'm letting you, sorry.
So here there's an exposure equivalent of 6 hours. It's not one long 6-hour exposure, it's a whole set of very short exposures, just 1 minute each. And then I've used a piece of software, there are free pieces of software that will do this for you, add all of the exposures together to give you the equivalent of one long 6-hour exposure. You can see that this is 6 hours by looking at how much the stars have moved. You see that each star has moved approximately 1/4 of the way around one full circuit. So 6 hours is 1/4 of a day, and hence each of the stars has moved through 1/4 of a full circle. Notice that in this particular case, Polaris is quite close to the pole, but it's not strictly speaking at the North Pole, and so Polaris itself is a little arc. although much shorter than any of the other stars that we can see. This particular set of star trails was taken from an observatory on the island of Tenerife, and so there are some observatory structures, domes on the left and other structures on the right, giving us a nice foreground for the star trails in the background. But as well as taking a lot of individual pictures and then adding them together to get the equivalent of a 6-hour exposure, alternatively we can add them together to make a movie showing the stars slowly rotating around Polaris. And again, the software that will allow you to make a long star trail allows you to make movies as well, where we're effectively adding each frame to the previous set of frames, so we get this impression of the stars rotating, of course due to the Earth's rotation. So it gives quite a pleasing result, either a static image of the whole star trail or a movie with apparently the stars moving in a sort of time lapse. Both of these are possible because digital photography makes it easy to take a series of short exposures and then play with them afterwards. Some of astrophotography is just being in the right place at the right time. So some of you might have been lucky enough to see the aurora as it came sweeping down towards England and the rest of the UK a little while ago. I didn't catch them myself from here in Liverpool. On those nights it happened to be cloudy. But I have caught the aurora before, in this particular case about 20 years ago, when I took a trip to Iceland and we were greeted by a wonderful display with the entire sky lighting up green because of the auroral displays. Again, this was long enough ago that this was before I had a digital camera. One of the problems with film cameras is they need rather longer exposures, and that tended to blur some of the detail in the auroral display. So one day I would like to go back to Iceland or perhaps somewhere else north of the Arctic Circle to actually try and catch the aurora borealis with a digital camera this time. Another example of having to be in the right place at the right time is a solar eclipse, even more rare than aurora. They only come round once in a while, and you have to make sure you're in exactly the right place on Earth. With aurora, you can be anywhere over hundreds of kilometers and still catch the aurora, but with a solar eclipse you have to be within a few kilometers of the right place to catch the disk of the moon covering the disk of the sun. This particular eclipse, excuse me while I dismiss the window. This particular eclipse was caught in 2006 when some friends and I decided to go and catch this particular eclipse in the Sahara Desert. We were prepared to go there simply to guarantee that we had sunshine. Rather than go somewhere which could have been cloudy, we decided to go somewhere which is known to be essentially cloud-free for a lot of the time of year where this occurred in March of 2006. It is a truly awesome sight, and if you ever get the chance of witnessing a solar eclipse, it is well worth it, regardless of whether you try and take a picture or not. So let's have a look at some of the admittedly rather ridiculously expensive equipment that you might consider buying. If you think that astrophotography requires a telescope, I'll say later that it doesn't, but if you did fancy buying a telescope, then what options are open to you? It depends how deep your pockets are. Now, if you've got plenty of money to spare, remember the Hubble Space Telescope has been around for over 30 years now, and it won't be too long before they decommission it. So watch out on eBay. I'm not sure what the second-hand price is going to be, but sooner or later NASA are going to have to decommission this telescope. And if you haven't got $1 billion to spare, which will get you wonderful images like these taken with the Hubble Space Telescope, the labelling there, M51, M16, these are just the so-called Messier numbers that are used to identify particular interesting objects in our night sky, star clusters or nebulae or perhaps galaxies. If you can't stretch to $1 billion, well, who can these days? If you've only got 100 million or so, then this particular telescope, it's an infrared telescope sitting in the back of a jumbo jet. The idea of putting it in a jumbo is you can fly it high enough that it gets above the atmosphere, which tends to absorb a lot of the infrared light. And this particular observatory called SOFIA, the Stratospheric Observatory for Infrared Astronomy. This 747, again, was decommissioned fairly recently. In the last month or two, it's been decommissioned because it's no longer required, or at least NASA have found it rather expensive to operate. So for a second reason, watch out on eBay in case this particular telescope in an aircraft comes onto the eBay market. If you haven't got 100 million, if you've only got £1 million or so, then there are smaller telescopes you could buy. For instance, a copy of the Liverpool telescope, which is sitting on La Palma. It's a fully robotic telescope, so you don't have to go to the Canary Islands to use it. If you've got a few $1 million or a few £1 million, you could buy one for yourself and take images of the pillars of creation or images of distant galaxies. But if we come a little bit further down to earth, if your budget is not millions or billions of dollars, if your budget is perhaps hundreds of pounds, then you have a lot of telescopes that you could think about. Indeed, it's a rather confusing market. If you're thinking of maybe getting into astronomy and thinking about what sort of telescope could I buy, then as soon as you have a few £100, your options are many and varied. If you have less than £100, quite often people suggest buy a pair of binoculars. But if you have a few £100, then you're into the territory of buying telescopes. And there's almost no limit to what amateurs will spend on their telescopes. It could be anything from hundreds to thousands. Some people make it a very expensive hobby by spending a lot of their free cash on astronomy hardware, especially telescopes. Some people like to buy a telescope and then buy all sorts of accessories to bolt onto their telescope and turn it into spaghetti, with extra telescopes on the side of the main telescope, plus cameras, plus all sorts of other things. Some people would argue that if you are going to be interested in astrophotography, what is really important, not simply the quality of the telescope, but the quality of the mount that is going to point your telescope at a particular object in the sky, and most importantly, follow that object. Remember, as the Earth turns, all objects in the night sky are going to appear to move in the sky, and if you want to take an astrophotograph over many seconds, or more likely many minutes or even hours, then it's very important that you can accurately track the sky. And so the quality of the mount onto which the telescope is put is just as important as the quality of the telescope itself. And again, some amateurs take this to what I would consider extremes in saying that you really want the most sturdy, most precise mount that you can afford. And some people might say, yes, it's worth paying thousands of dollars or thousands of pounds to get the best possible mount, even before you think about the telescope. Well, if your pockets are that deep, that's fair enough. But I assume that anybody who wants to get into astronomy is more interested in buying a telescope for perhaps a few £100 rather than many, many thousands of pounds. And if you're in that position, especially by the end of this talk, if you're interested in getting into astronomy and buying a telescope for yourself, excuse me whilst I dismiss that.
Sorry.
It's okay. If you're interested in getting into astronomy and buying more telescopes for yourself, then I have a separate talk which is a sort of a rough guide to what you need to think about if you're interested in buying an astronomical telescope, regardless of whether you're interested in astrophotography or whether you're interested in just looking through the telescope at various objects in the night sky. I will send that link to Sandra and Sian just so that you have that if you wanted to go and watch a recording of that particular short talk. But if you are going to buy a telescope, one thing you've got to think is, where are you going to put it? In your back garden, or are you going to think about an observatory site? Now, it would be wonderful to have an observatory like this. This is Palomar Mountain in California. I visited this back in 1982. There I am as a student. It looks like I'm actually wearing the same shirt as I did back in 1982. But that, at the time, I went to see the 5-meter Hale telescope, a telescope with a 5-meter diameter mirror, the largest telescope in the world at the time. And I was so impressed by that, I thought, yep, that's a fantastic telescope, that's a fantastic domed observatory. When I grow up, I'm going to have a house with a back garden big enough for an observatory like that. Okay, I had to downsize my expectations a little bit, but in the late 90s I bought a house with enough room in the garden to build myself an observatory. It might look like a shed, but okay, it's a converted shed in which I had one of my telescopes set up. You can tell this is a relatively old picture because A, the shed is quite clean, and B, the laptop sitting behind the telescope there looks like a brick. That tells you that this is not a modern state-of-the-art laptop, but something about 20 or so years old. And the idea of having a telescope in your back garden is quite attractive because it's basically always there and you don't have to set it up each time you want to do some observing. And with a telescope, of course, you can get wonderful views of stars and planets, but even the moon, you shouldn't ignore the moon. It's our closest neighbour, but it still can be fascinating to watch the shadows of the craters and the mountains change essentially from hour to hour as well as from night to night. So, okay, the moon is not always visible, it's not always clear in the United Kingdom, but whenever we have a clear sky, you should not forget that the moon sometimes drowns out some of the faint details of objects in the night sky, but the moon itself is a very interesting object. And that was photographed through the telescope that I showed on the previous slide. But rather than talking about ridiculously expensive equipment and very expensive telescopes, I wanted to talk about equipment which is a little bit cheaper. In other words, using cameras on a star tracker. A star tracker is basically a device that allows you to move the camera to follow the stars. But before we talk about that, let's just remind ourselves how images are obtained. If we want a colour image of an object, there are essentially two ways of doing it. We can start by collecting light, it doesn't really matter if it's from a lens or a mirror, and focusing the light onto either film or a CCD chip in a digital camera. And black and white film and also monochromatic CCD cameras do exist, although you tend to think of most cameras as being colour cameras. A lot of cameras that are used in astronomy are actually monochromatic, they are just black and white cameras. And if you want to obtain a colour image, you would put a red filter and then a green filter and then a blue filter in front of the chip and take three separate images, red, green and blue, and then combine them into a colour image. But for some people that's a little bit too much like hard work, and so they would prefer to use a one-shot colour camera. In other words, a single exposure gives you a colour image. Now with film, that meant the film had to be a particular type of colour emulsion that had embedded in it the filters necessary to give you a colour image. With modern digital cameras, the chip actually has a set of red, green, blue filters actually manufactured in front of every pixel of the chip itself. In other words, if we were to zoom into a chip and have a look in detail at what's going on, we would find individual pixels which had red filter, green filter, blue filter in this particular pattern called a Bayer grid. And so the actual image obtained by the camera would be a whole load of red pixels, a whole load of green pixels and a whole load of blue pixels. And obviously there are some gaps there because we don't take the same colours at every pixel. Each pixel has its own dedicated colour, and so the software would have to effectively fill in the gaps. But that's how colour imaging is done with most digital colour cameras. So here's a selection of some cameras that can be used for imaging. Even the cheapest camera that's used for astronomical uses might be perhaps a few £100 or so, and there is almost no limit to how much you can pay for a camera that's dedicated for astronomical use. So for instance, a camera with quite a few million pixels in it might be a few £1,000s. And even a monochromatic camera, that might sound a bit paradoxical, but even a monochromatic camera might be the same sort of cost. This is basically because it costs very little to add the filters onto the front of a particular CCD device. And if you did use a monochromatic camera, then you would need to place filters in front of the camera in order to obtain colour images. And it is quite common for amateurs to use a so-called colour wheel. In other words, filters which let through different colours would be on a filter wheel which can be motorised to rotate and place a particular filter in front of the camera. So the camera might be instructed to move a filter in front of the camera and then take a particular exposure, and then move a different filter in front of the camera and take another exposure. And if that's done for red, green and blue filters, then you can construct a colour image. But I'm talking about not using ridiculously expensive equipment. And for most of us, we might already have a camera. For instance, I have a digital SLR camera because I like taking pictures quite often of wildlife. For instance, you've seen my wildlife photography talk from a little while ago. So I'm interested in using a camera, either with a wide-angle lens or perhaps with a telephoto lens, to take pictures of either my family or to take pictures of wildlife, either here in the UK or on holiday on safari. So if you already have a camera, you don't have to invest in an astronomical camera. A camera that's designed to work in daylight, actually, perhaps surprisingly, is often very good at taking pictures in an astronomical context. And to do that, you still have to be able to get the camera to follow the object in the sky. If you want to take a long exposure, you can't just have a camera fixed on the tripod, otherwise the stars will trail. And so you can use what I call a star tracker, what are generally available as star trackers. You can either build one for yourself. For instance, the picture on the left is a star tracker that I designed and built and have used for quite a few years. If you're interested, I can make the instructions of to how you go about building yourself a star tracker. Again, I can make that available by emailing you the links to where you can find the information. So you can build yourself a star tracker for perhaps £10 or £20 or so, or you can buy yourself a star tracker, and that's a particular type of commercial star tracker that's available and has been available for many years. And there are various manufacturers that make these things. That particular one is made by a firm called Ioptron, but there are 2 or 3 or 4 or 5 other companies that make similar star trackers. And in essence, a star tracker is just a motor in a box. It isn't really much more sophisticated than that. It's a motor in a box that's designed to drive the camera and rotate the camera at 1 revolution per day. And hence, if it's set up correctly, as the sky appears to rotate because of the rotating Earth, the tracker will move the camera and follow the stars. So the idea is you take your camera with your wide-angle lens or your telephoto lens and you bolt it onto the front end of your tracker, and all you have to do is to make sure that it's lined up parallel to the Earth's axis. And the easiest way to do that is, because Polaris is so close to where the Earth's axis is pointing, you simply find Polaris in this little polar scope on the side. And that allows you to get very close to lining up parallel with the Earth's axis, and then the motor takes care of rotating the camera. So that's what I have done. I've used wide-angle lenses, I've used telephoto lenses on this particular tracker, this motor in a box. And that's all it is inside. It's relatively straightforward. It's batteries feeding a little bit of circuitry which feeds a motor and a gearbox and a worm drive, which ultimately will rotate this large disc which is connected to the camera. It rotates this precisely at 1 revolution per day to make sure that the camera follows the stars. So let me show you what you can do with a camera and a star tracker. I'm not going to go through pictures that I've taken with telescopes because I like to take astrophotographs without using a telescope. I want to see just how much you can do just using a camera and a wide-angle lens or a telephoto lens on a star tracker. Some of these images were taken from the United Kingdom, some of them were taken from dark sky sites, but it shows you that you don't need particularly specialist hardware if you want to get into astrophotography. In principle, if you already have a camera and some lenses, or a zoom lens perhaps, then with a modest investment of a few tens of pounds, or at most a few hundreds of pounds, you can take pictures like this. The beautiful colours that you see here are genuine colours. It's difficult to see these colours with the naked eye simply because our eyes are not designed to see colours in very low light. The cones, the red, green, blue cones at the back of our eyes are designed to work in bright light, effectively in sunlight. And as soon as that light drops, for instance in moonlight, we tend not to see colours. But cameras are very good at picking the colours up that are there. So we can see different coloured nebulae here, and even here we see the blues and pinks of this particular nebula. Galaxies tend not to have that much colour in them. There's a great many stars contributing to this image of the galaxy, and all of the star colours tend to blur into a sort of a beige sort of background. Here's a wide-angle shot of the Milky Way, and this is a shot, I'll show you more detail later. This is a picture of a supernova that went off tens of thousands of years ago, and this is the supernova remnant that is left. And it was taken, most of these were taken with this camera, a digital SLR camera with various types of lenses on them. So yes, you can, if you wish, buy yourself a telescope and do astrophotography by taking images through a telescope rather than on a star tracker. And that can be enormously rewarding. And perhaps you've seen some astrophotographs taken by amateurs that are absolutely spectacular. But to get the most out of astrophotography with a telescope, it will take a bit of time, it will take effort, and it will take cash. And I'm trying to get the focus of this particular talk towards what you can do without outlaying too much money. So just a little bit about what you do with the images you take. Don't expect to point your camera at the sky, take a snapshot and get the sort of images that you see on web pages or in magazines. If you take a picture, in this particular case I've taken a picture of a nebula in the constellation of Cygnus, it is not surprising that the first thing you get is an image that appears rather washed out, and in this particular case it seems to be completely orange. And that's simply because it was taken in a situation where there was some light pollution in the sky. Your eye doesn't always see this light pollution. Maybe you look up into the sky and it looks quite dark. But the camera is quite sensitive to light reaching it, and especially the colours reaching it, and the camera will pick up from the fact that the sky is not black, it is not even dark grey, it is quite often slightly yellow or slightly orange, depending on what street lights you have close to where you took the image. But that isn't necessarily a problem, because even though your raw image might look a little bit like the image on the left-hand side, software is very good at processing images and bringing out the detail that exists. So this is the nebula that I was trying to photograph, which is very difficult to see. Perhaps you can just make out the outline there on the left, but of course it's very much more difficult to see because of this orange colour cast. But in software, and again there are software packages, some are free, some cost money, there are software packages that help you bring out all of the detail that's in your astro images. And in this particular case you can see why this hydrogen nebula is called the North American Nebula, because you can see its outline bears a resemblance to the North American continent. And you can start to see some of the colours within the nebula, and you can see the fact that different stars have different colours as well once you start doing a little bit of image processing. So remember, you can't just take the raw image and expect it to look beautiful. You do need to do a little bit of processing to bring out all of the beauty that's hiding within these images. So here's a picture of the so-called Rosette Nebula. This is in the constellation of the Unicorn, sitting next door to the constellation of Orion that's visible during the winter. This particular nebula is effectively a sort of a nursery of stars. It's a large cloud of hydrogen, which is why it's glowing pink. If you take hydrogen atoms and excite them, they tend to radiate light at the red end of the spectrum. So when you see a cloud like this looking pink, you know it's composed primarily of hydrogen. And this hydrogen cloud is a sort of stellar nursery, and stars are being born in the centre. Some of these stars here in this cluster have been born out of the hydrogen cloud that we can see there. At the bottom of these images, I'm indicating which camera I used to take the image, what the lens was, in this case a relatively modest telephoto lens of 300mm focal length, and what exposure did I give it. I would like to expose for a long time, but I can't always track the object accurately enough to take a 1 hour exposure, so I take a lot of short exposures, in this case a large number of 30-second exposures. That has the advantage that I don't have to track the object very accurately. It also has the advantage that if a plane or a satellite happens to cross my field of view, I only waste one image and keep all the others. And if any cloud happens to roll by, again, I can just throw away those images that happen to have cloud in the way and keep all the ones that were nice and clear. So there's lots of advantages to taking a large number of short exposures rather than a small number of long exposures. So here's another nebula. This is at the other end of its life. This is not a nebula that's producing star birth. This one is actually the result of star death. This is a nebula that's the result of a sun, much like our own, that's expanded at the end of its life when its fuel is running out, expanded until it's a red giant, and then the outer part of the star's atmosphere has been blown away into interstellar space and produced this somewhat bluish and orangish nebula. And although the stars look a little bit large, they should really be points, and this isn't a terribly good image. It's an image from quite a long time ago when I was still learning my craft as to how to take astro images. The stars themselves are a little bit bloated. But I took this image, and it's in the constellation of Aquarius, low down in the south during the summer months. I took this image because I was interested in seeing just how much I could catch with my camera and compare it with the image taken by the Hubble Space Telescope of the same object. Now, of course, the stars are much more like pinpricks in this image from Hubble, and so that's one of the reasons the Hubble image is better. Also, there's far more detail in the Hubble image of the actual nebula itself in terms of the structure and the beautiful blue inside and the orange outside. I can get the hint of the colours, but I can't get the sort of detail that Hubble is able to produce. But my camera cost hundreds of pounds. The Hubble Space Telescope cost billions of dollars. So there's a huge difference between the amount of hardware taken the image on the left and the amount of hardware that took the image on the right. We can never, as amateurs, expect to rival the images produced by Hubble, but it's still fun to photograph the same object and say, well, can I see the same stars? Can I see anything of the object itself that resembles the Hubble picture? We're not trying to do better than Hubble, but isn't it great fun just to see what we can get? This is a supernova remnant. The Veil Nebula in the constellation of Cygnus is a star that blew itself apart tens of thousands of years ago. We're not sure where that star is. Maybe there's no sign of it at all in the centre here. We can't identify necessarily the original core of the star that blew itself to pieces. There will be very little that's left. Could even conceivably be a black hole, in which case we can never see the star itself. But the material thrown out from the supernova has been expanding for thousands of years, and we get this vague impression of a sort of bubble. in much the same way that in a soap bubble we can't always see the bubble, but we can see the edges of the bubble. It's the same idea. This is probably a sphere, but we can only really see the left hand and the right hand edge, and perhaps some of the other regions. Perhaps this is part of the bubble that's coming towards us. Perhaps this is part of the bubble that's moving away from us. The more we look, the more we can see fine detail in terms of the nebulosity, but the most striking features are the fact that we get these rather dramatic shock waves as the material that's ejected from this supernova are travelling outwards, ploughing into the material that's in between the stars, the so-called interstellar medium, and that gives us these rather interesting structures. And the colours are coming from the fact that I mentioned earlier, hydrogen tends to glow red. That's what's producing the red in these images, but clearly there's a lot of a sort of bluey green, a cyan colour in there as well. That's because this nebula has got a great deal of oxygen in it. And again, when the oxygen atoms are excited, they tend to produce light in the green-blue part of the spectrum rather than hydrogen, which produces light in the red part of the spectrum. So simply looking at the beautiful colours that are produced in these objects, not only can we say this is very aesthetically pleasing, we can also effectively say, well, I can now tell what this nebula is actually made of. I know that there are hydrogen and oxygen atoms in there. And if we were to look in more detail, I'm not going to delve into this, but if we were to look in more detail, we can find other atoms are present as well, and hence we get a good idea of what stars are made of. This is an image I took from a relatively dark sky site. This is not taken from the UK. This was taken when I was taking students over on a field trip over to the Canary Islands. This is part of the constellation of Scorpius. This is the star Antares, which is a very large star which is lighting up the nebulosity around it, which is making it glow sort of yellowy orange. Next door to Antares, or at least next door in terms of our line of sight, there's a rather large star cluster. The stars are so crowded here that I can't make out individual stars. There are probably 100,000 stars in this cluster, most of which are too close together for me to separate with my camera. And there's a triple star over here called Rho Ophiuchus, and that is a blue star, a triple star that's lighting up the nebula around it, producing this nice blue glow. But you notice that in addition to a lot of stars in the background, we have some dark clouds as well that are blocking our view of the more distant clouds. You can see in this region up here, for instance, there seems to be a large brownish cloud which is blocking our view of the clouds of the stars in the background. There should be as many stars as we can see here also visible in the background, but this dust is simply blocking them. So we have some gas and dust that's being illuminated by stars, and we have some gas and dust which is blocking our view of more distant stars. And understanding molecular clouds like these helps us understand how stars form. And it's just nice that in this particular view, in this constellation of Scorpius, we get a few contrasting colours as well as the dark clouds to give us nice contrast. This was taken with a 135mm lens, a very modest focal length again. There aren't that many galaxies that we can photograph. We live in a galaxy called the Milky Way, and we can take pictures of that from the inside. But if we want to take a picture of other galaxies from our vantage point, then we can't think about galaxies that are too far away. The observable universe might have trillions of galaxies in it, but most of them are so remote we can't expect to photograph them without a telescope. But even with a camera and a tracker, here again with a 300mm lens, I've managed to capture the Andromeda galaxy. This is one of our nearest neighbours. We have a number of small galaxies around us, small satellite or dwarf galaxies. This is one of the largest that is at the distance of about 2.5 million light years. Close enough to us, one of our nearest neighbours, such that Andromeda makes a very nice large object in the sky. The field of view we're looking at here is substantially larger than, for instance, the diameter of the full moon. If the full moon was in this picture, it would fit inside this image something like 10 times. In other words, it's about 10 diameters of the full moon. This is quite a large galaxy. And with a long enough exposure, in this particular case, I've taken 30 images, each of which was 1 minute, and then added them together. And you can see, not only can we pick out the bright nucleus of the galaxy, and it also has a couple of satellite galaxies of its own, but we can see the spiral structure. We can see the spiral arms whizzing around like a whirlpool around the Andromeda galaxy, and we can see these dark dust lanes visible where, again, material within the galaxy is absorbing some of the light from more distant stars. So it's very aesthetically pleasing to be able to take a picture of the galaxy like this. Unfortunately, there are not that many galaxies that we can photograph. There's only really half a dozen that are good candidates for a camera. If you want to take pictures of the other hundreds and thousands and tens of thousands of galaxies, then unfortunately you do need to invest in a telescope. And possibly the least remarkable looking image that I took, I've taken during a lockdown. During the lockdown of 2020, we were looking down at our feet, but Stephen Hawking was telling us not to look down at our feet, but to look up at the stars. And I wondered, what is the most remote, what is the most distant object that I can ever hope to photograph with my camera? So again, I put my camera on this tracker and photographed a chunk of sky where I expected to find a very remote object. It's not the bright star at the centre there, that just happens to be a star in our Milky Way. I was expecting to see the nucleus of a galaxy somewhere, hopefully in the middle of that square. In other words, I looked up somebody's research paper that said they found a very bright galaxy, a very remote bright galaxy, and they gave its position, and so I tried photographing this particular field of view. And if I blow up what I saw in that square, then it's the least remarkable image that I'm showing this evening, but that object there, indicated by the two red lines, is a very, 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 very distant galaxy. It's called a quasar, which is just another name for a galaxy which has a very energetic nucleus that's emitting a great deal of light. And it's emitting so much light it can be seen, even though this object is effectively on the other side of the observable universe. Most of the light from this quasar is in just 1 pixel of my 20 megapixel camera. So there it is, blown up a little bit bigger. I've got 20 million pixels in the camera, but this quasar occupies perhaps just 1 or maybe a few of those pixels. And the most incredible thing about this, the picture itself is unremarkable, but the facts that are connected with this object are truly amazing. It's at a distance of some 25 billion light years. It's difficult enough to imagine distances to stars of light years, or distances to galaxies of millions of light years. But this object is thousands upon thousands of times more remote than the Andromeda galaxy that I showed just a moment ago. The universe is expanding, and these galaxies are moving away from us. They are receding from us. This particular galaxy is so far away from us, and the universe is expanding so fast, this galaxy is actually receding from us at twice the speed of light. This is just absolutely remarkable. The fact that it is possible to image an object 25 billion light years away, moving away from us at twice the speed of light. The light to get to my camera has been travelling for some 12 billion years. That's most of the age of the universe. The light that produced that little spot there left this galaxy long before the Earth even existed. 12 billion years is something like 90% of the age of the universe. So the light left this galaxy soon after the universe was born, and it's been travelling all that time before it finally arrived in my camera to produce that spot. A most unremarkable spot, but a most remarkable journey for the light to create it. Let me finish with how you can take pictures under the darkest of skies. Perhaps you're happy to stay in the UK and admire the night sky if you're lucky enough to live somewhere away from street lights. I'm not so lucky in that I have a street light right outside my house. But if I do manage to go on safari, then I have the best of both worlds. I like to watch wildlife, I like to take binoculars for astronomy, I like to photograph wildlife, and here we're talking about photographing astronomical objects. And all of these interests combine if you go on safari, because you get the wildlife and you get the dark skies, because if you visit, for instance, parts of Africa, you can get hundreds of miles away from the nearest streetlights. So in other words, that holiday is taking pictures of animals by day, stars by night, and sleep when you get home. Don't waste your time when you could be taking pictures of animals and stars. So I take my tracker with me. Now in the UK, it's easy to make sure that your tracker is lined up with the Earth's axis, because you simply point the telescope in the direction north and you make sure that Polaris is in the right place. In other words, an app on your phone will check where you are and what the time is, and will tell you that if you're pointing at the North Pole, Polaris should appear in your polar scope at this particular position. And so you simply adjust your tripod until Polaris is where it should be. That's fine if you're in the United Kingdom, but if you go to East Africa, there's a problem. So the Earth is turning with its axis pointing towards the North Celestial Pole, and from mid-latitudes you can see Polaris in the sky 50 or so degrees above your horizon. But if you're on the equator, then Polaris is basically on the horizon, and hence it's going to be hidden behind elephants or hills. So you can't line up and make sure that your tracker is lined up with the Earth's pole by using the pole star, because you simply can't see the pole star. So you have to find alternative ways. You have to just make sure that your tracker is pointing north as best you can tell. And whilst I was there in Kenya, I took a picture of the Large Magellanic Cloud. This is one of the satellite galaxies of the Milky Way. The Milky Way is a large galaxy. It has a large number of small galaxies in satellites around it. And this is the largest of the Magellanic Clouds. The Large Magellanic Cloud, again, it didn't need much of a telephoto lens. I had to back off in this case to an 85mm lens, because the Large Magellanic Cloud is indeed so large in the sky. I wasn't sure that I was quite lined up correctly, so I couldn't guarantee that I was tracking the Large Magellanic Cloud accurately. So some stars are not quite pinpoints, but still I managed to get a pleasing picture of the Large Magellanic Cloud, which is not visible from the United Kingdom simply because it's too far south. So I took advantage of being on the equator to take pictures in the southern hemisphere. And the Milky Way itself, again, from here in the UK, sometimes it's difficult to see detail within the Milky Way. You have to go outside on a clear night and let your eyes adapt. And even then, sometimes the Milky Way is not as clear as it should be. But if you get away from light pollution, then the Milky Way is absolutely glorious. And even with the naked eye, you can start to see clear structure. The centre of the Milky Way is somewhere around here. And again, you can see dark tendrils of dust lanes that are obscuring the light from more distant stars. And the more you sit and watch the sky, the more your eye can pick out the detail in the Milky Way. But even at the best of times, your eye will not pick out the colour. But by taking pictures, in this case with a wide-angle lens and a series of 2-minute exposures, then you can start to realise that the Milky Way is indeed full of colour, and your colour camera will start to pick that out. This is just for comparison. This is a picture I took many years ago with slide film before I went digital. And in this particular case, I photographed the constellation of Scorpius. Perhaps you can see the front of the scorpion, the back of the scorpion, and there's the curved tail, and there's the sting in the tail of the scorpion. But with slide film not being very sensitive, I could pick out the brightest stars, but I couldn't really see much of the Milky Way. But with a digital camera, it's just the opposite problem. It is so sensitive. With digital cameras, we can pick up so many stars, it's actually difficult sometimes to pick out the brightest of stars. So the constellation of Scorpius here is visible in this picture. It's just difficult to pick up because there are so many faint stars. But if I join the dots, perhaps you can see there's the constellation of Scorpius once again. So this brightest star here is Antares, the one I mentioned just a moment ago, and here is Antares in this image. So that's something to bear in mind. You pick up so much in these images, sometimes the brightest stars don't make themselves as visible. And this is just a crop of the previous picture to show that there's a great deal of detail in here. The bright object near the center is actually the planet Jupiter, and over towards the left there's the planet Saturn. They are now in rather different positions in our sky simply because this picture was taken a few years ago. But notice that we can see a lot of detail in the Milky Way, and the more we look, especially if we compare it with a star atlas or an app that tells us what's in the sky, we realize that not only have we got 2 planets in there, we actually have lots and lots of star clusters and nebulae and other objects that we can identify. Some cases we can simply zoom in and see more detail. In some cases we simply have to compare with an atlas or an app to tell us what these star clusters are. All of them have already been catalogued, sometimes centuries ago. For instance, the 18th century astronomer Charles Messier identified and labelled a lot of these star clusters and nebulae, and he gave them M numbers, M1, M2, M3, etc. And we can see a number of them here. Notice that they seem to stop at a particular point. That's not because there aren't any interesting objects south of that line. It's simply because Charles Messier worked from France, and there's a limit to how far south you can see from the south coast of France, and therefore he couldn't see any further south than that line. Hence all the objects that he has identified and catalogued are north of that particular line. I wondered how much detail I could get from this particular pair of nebulae. There's a couple of nebula inside that red rectangle. They don't show up too well with a wide-angle lens because they're not really big enough. But then I thought to myself, well, instead of using a wide-angle lens, why don't I switch to a telephoto lens and see what they look like? And this is a single 30-second exposure. So this is not a very long exposure. It's not a large number of short exposures. It's just a single 30-second exposure which shows more detail than can be seen in that red rectangle. The Lagoon Nebula is at the bottom and the Trifid Nebula is towards the top there. And if we blow up the Trifid Nebula just so you can see more detail, you can see the beautiful colours of the blue and the purple that show up in this nebula. And that, remember, is just a 30-second exposure. So you don't have to think of astrophotography as being very, very long exposures, though sometimes that helps. So the take-home message for this talk, I guess, is you can do astrophotography not exactly on the cheap, but you certainly don't have to spend many, many hundreds of pounds or thousands of pounds. You can do some astrophotography if you already have a camera. You can build yourself a tracker for 10 or 20 pounds, or you can buy yourself a tracker and then you can take images, providing you get away from light pollution. You can take images such as the one shown there. And that's why whenever I go on holiday, I take a camera with me, hopefully to photograph the wildlife, but also I take a tracker with me. It adds very little to your luggage. If you take a tracker as well, and you can get away from the light pollution that plagues part of our country, then you can take beautiful astro images whilst you're on holiday. I hope you've enjoyed that ramble through my take on astrophotography.